Put 1,000 jobs into 1,000 server queues. In a repeatable local run, if each job picks one queue at random, the luckiest queue reaches 6 jobs. Give each job a second random choice, and the tallest queue reaches 3. Same work, half the worst backlog. Why can one tiny extra sample change the tail so much? This is the balanced allocations problem. Imagine identical servers as bins and incoming jobs as balls. A load balancer has to choose where each ball goes, but it may not have time to inspect every bin. With one choice, it samples a server and sends a job there. That rule is almost free, but leaves every unlucky draw in place. Watch the one-choice process. The first job spread out. Then a few random hits land on the same bin, and that bin becomes taller. The next job does not get to reject it. A random process is fair on average, but the maximum is controlled by its luckiest streak. In the classic model, the tallest bin grows on the order of log n divided by log n. Now, change only one line of the algorithm. For each new job, sample 2 servers at random. Read their current queue lengths, and send the job to the shorter one. You still inspect only 2 servers, not the whole fleet. If the pair is tied, break the tie randomly. The second sample is not a perfect global view. It is just a chance to refuse the worst of 2 local options. Here is the surprising step. Suppose only 10% of the bins are already at height 5. Under one choice, a new job reaches that high region with probability about 10%. Under 2 choices, it reaches height 6 only when both sample bins are already at least 5. That chance is roughly 10% times 10%, 1%. At the next height, the same squaring happens again. A tall queue becomes hard to extend, so the tail thins much faster than the average suggests. Run both policies on the same 1,000 jobs, with the same seed and the same 1,000 bins. One choice ends with a maximum of 6. 2 choices ends with 3. That small experiment is not a proof, but it mirrors the theorem by Azar, Broder, Carlin, and Upfull. With high probability, the asymptotic maximum drops from about log n over log n to about log n over log 2, plus a constant. The improvement is not a nicer average. It is a much shorter worst queue. The rule matters when the view is incomplete. F5's and Jinx explanation describes independent load balancers that each see only part of the traffic. If every guide sends requests toward the one queue that looks briefly best, they can herd together and overload it. Sampling 2 queues and choosing the shorter avoids the worst option while keeping enough randomness to spread decisions. A stream processing paper used the same idea with key, splitting, and local load estimates because real workers can be stateful and their loads can be skewed. So the algorithmic lesson is not random is always better. It is more precise. When a perfect global comparison is expensive, 2 independent samples can buy a dramatic reduction in the worst tail. Use the rule when jobs and servers are comparable and a current load estimate is meaningful. Add a stateful or skew-aware adaptation when they are not. One choice accepts whatever luck gives you. 2 choices let every job reject the worst of 2 futures.